it's actually essentially a progress report on a very long project that, of course, I've been thinking about for many years. Is the original question was, we have these mirror pairs that constructed with Mark many years ago, and how do you prove homological mirror symmetry in some form for these pairs? Okay, but over the years, well, actually, I had many discussions with Mohammed from 2012, maybe to 2017 or so, until he finally, we finally agreed that this project will never surface, and he moved on to other things. And fortunately, I have a new co-author on that, and Tim Perutz. One of the benefits of moving to Austin. And many things have happened since this original question that made me a lot more hopeful that we're actually getting very close. Let me say what the advances are. So first, there's finally something that I believe, is safe to use on the virtual fundamental classes. There have been several approaches, and the one that speaks most to me is Pardon's BFC formalism. Of course, there are many others, but this is something that I can see I can use very efficiently, and it will work well in the setup. The other is there have been many advances on symplectic cohomology. So back in maybe 2012 or so, the literature was rather limited. Now we have all these things that I can look into and see, okay, I just have to copy and modify a little bit. Notably, I mean, many foundational work, of course, by Groman on compactness issues, and by Terani, McLean, Zinger, on understanding normal crossings in symplectic geometry. And then notably also by Ganatra and Pomigliano, which is very close in spirit to what I'm going to talk about for pairs x, d, assuming x minus df. Then there are generation criteria for the Fukaya category. Starting with Mohammed, and I will tell some other version that has been done by Ganatra and by Perutz and Sheridan, and also by Ganatra. And then on our side, we finally understand much better how to work with punctured Gromov-Witten invariants. It's a long collaboration with Dan Abramovich and Chile Chen, Mark Rose, and that led to intrinsic mirror construction. Unfortunately, a rather long paper that has been out since last September. So taking all these together, there is some hope to actually proving, to going to showing that f of x is actually equivalent, infinitely equivalent to the dvo of the mirror side. Okay, so let me start with explaining a little bit about these intrinsic mirror pairs, or maybe more appropriately for today's talk, let me sell this as a version of quantum cohomology, actually just degree 0 quantum cohomology for pairs x, d. because this is really what we have been doing. This is kind of a joke that the thing that's kind of went at the very beginning of mirror symmetry and quantum cohomology actually seems to be really at the core of understanding mirror symmetry, and it's all in there, but with an interesting twist. So we start with a pair x comma d, and the only assumption I make is that the logarithmic canonical bundle should be effective, be supported on D. So the most favorite situation is, of course, if x comma d is a log Calabi-Yau pair, where the right-hand side is 0. But this goes, this is a good condition from the point of view of some, we don't need minimal models. It's a lot more general.
You see it's supported on D.
It's on D, right? So D is
DI components of D.
DI are the components of D. And D is normal crossings. Okay, X smooth, of course. And so I call this the absolute case. And for homological mirror symmetry, I can tell it quite a bit more about what is the kind of more traditional case, where I have a degeneration. So X to S, so that would be just some perimeter space curve, and then the XD is just the total space in the central fiber. Okay, so and that's problem. So it's non-compact, but we have this nice morphism to S that simplifies the situation. So then given that, we can build something called the dual dissection complex. So that has a simplex. Actually, I just take a cone here. So R larger equals 0 to n, the simplicial cone, one for each zero-dimensional stratum. So this is just di0 intersected din is non-empty. And it has an integral structure. So just the integers in here, into z to n, larger equals 0, that I want to view as carrying contact orders of curves with a boundary. So what I mean by this, let's think of something like P2. Then I just have these, what looks like the fan of P2, but you should really think of this as just being union 3 copies of R2 larger equals 0. And then the point here, for example, let's say 2, 0, that would be an order 2 contact here, or something like 3, 2, could be something like a mu parabola going into that deepest stratum. Okay, so the integers here contain these contact orders of curves. And then I build a ring, so which is this QH0 XD, by taking generators given by these integral points. So the ring is direct sum R times theta P, and P are the integral points. Note that the origin also makes sense, right? That would be a point in the interior. Okay, so and then what is the coefficient ring? R is a kind of, actually I don't need C. We'll go with rational numbers. And then it's some completion of the curve clauses, effective curve clauses on X, or some finally generated version of that. Okay, so these will contain curve clauses. And then of course, so that's the module structure, and then of course the question is, what is the multiplication? And that's the sum over contact orders R in classes beta. And let me put a comma here. P, Q, and R are slightly asymmetric. So So beta contributes with t to beta. That's a monomial in here, in this coefficient ring, and then we have the theta r. Okay, so that is the rule. And the NPQR count curves. With two positive and one contact order that is kind of less or equal to. And you wonder how this makes sense. So the NPQR beta. I'll give an example to show you, illustrate what this is. So you look at curves, genus zero curves, class beta, 2 my x comma d, and I want the 2 points, just ordinary contacts PQ as in logarithmic theory, but the third point is a bit strange. I prescribe minus r, okay? So what does this mean to say minus r? So let's do an example. Let's compute that mirror. So of course the theorem that is then is that this ring structure, let me put it down maybe first, is associative. It's associative. Associative cumulative ring. And the idea, of course, it is totally simple. It's what you know from the WDVV equation. You just look at the moduli space with 4 more points. But the subtleties of logarithmic gluings and make this a very long paper, unfortunately. Yeah, but the idea is totally simple. Okay. That's exactly as you think it should. Okay, so let me look at an example. So what is the mirror of P2 with union 3 copies of P1? Well, you get different mirrors depending on what kind of D you take. Okay, so I have to be precise and say I'm doing this. So let me draw that diagram again. So this is your P2. This is the B. And I claim that the ring you get, the result you get if you do it, is x, y, z, damn it, t here. So Q, we have one curve class T, and then x, y, z, and the single relation x, y, z minus t. Yeah, let's look at this equation x, y, z equal t. Of course, that's not a 3-point function, it's a 4-point function. And it would indeed count curves where you fix 1 point here, that's the outgoing point, corresponding to this t times 1. And then you look at curves, let me draw them like an amoeba, lines with contact orders 1, 1, 1. Okay? These are the x, y, z. I haven't said what x, y, z are. So the x would be, in my notation from before, theta 1, 0. The y is theta 0, 1. And the z is theta minus 1, minus 1. Okay, so these are these 3 generators. How do we get this in terms of the 3-point function definition? So we'll have to do a few computations, right? So we have to, how do we get x, y equals t? So that comes from, let me get another blackboard. So we first compute x times y. I want to get theta 1, 1. Sorry, yeah, theta 1, 1. No, that's wrong. Theta minus 1, minus 1.
No, that would be z.
Let me see.
Pick one.
I want this one. I want theta 1, 1. Yeah. Yes. Okay. So that would be the tropical diagram. So each of these curves that I compute will have tropicalizations. They look like ordinary tropical curves, except the outgoing point doesn't have a ray. Yeah, so the incoming ones have rays. These are the P and Q. But the R is actually going in the negative direction, so it's not going out, right? So R is pointing in, and there's no positive contact. So what would this mean in terms of geometry? It means that you have a contracted curve. You know, so there are no curves of negative contact, but if you measure contact in terms of degree of line bundles, of course, if you have a contracted curve, you can have negative line bundles. Okay, so this would be a curve where everything gets contracted to that point here. And it just happens that the contact orders here at P and Q prescribe first order contact here, first order contact here, and the R is kind of a negative contact in the other direction, okay, which you can't see, cannot draw. But such a stable log map exists, or punctured log map. So this is the first thing, and then we want to see that theta 1, 1 is the inverse of z, right? So we want theta 1, 1 times z is up to this t. And that would be where you now have to go through the origin tropically. So you would start with something which would be this r. Sorry, that's a p now. And then the r is 0, and then we have the q here. So what are these curves? No, the r is in the origin, and then we have these contacts. It's a line like this. Okay, so this roughly gives you an idea of what these ring structures are. And hopefully that already reminds the more symplectically oriented people in the audience of symplectic homology as a product structure, the pairs of pants product structure.
Can I ask a question?
Yeah?
From this point of view, is this red thing part of the proof of like WDBV or something of associativity? I mean, because you said XYZ equals T times 1, you can see that because of this curve. But this curve has 3 inputs and 1 output. Mm-hmm. And then you somehow actually proved it.
Yeah, you're right. I mean, that would appear in the proofs.
I mean, the actual one that you would need, shouldn't that be instead of a line that passes through the corner? Should you find this as x, y, z?
No. No. Well, I didn't want to make the you have to fix. Well, there are choices. You have to fix the cross ratio of the 4 points, right? Just as in WDVV. So you have a P1, and then I fix 0, 1, some point u infinity. What you want is a degenerate situation where actually your curve would split. So if you move that point into the origin, you would have a contracted component. I don't want that at the moment.
Yeah, but the point is, if you want to see this as a single
to see
product,
for the proof, I would exactly. I have a one-dimensional moduli space, and both this one and the one you were thinking of appear in Z.
That is xy times z. It's one boundary of the modulus.
It's one boundary point.
Oh yeah, that's
yes,
yeah.
okay.
And this
yes,
one
yes,
appears
yes.
when you try to prove that it's equal to the other composition.
So for coefficients of 1, you don't have to get this negative tangency to the normal tangency.
Exactly. And these are the only ones where you actually have traditional counts. Yeah. And that relates to the work of Tony Yu and Sean Keel. They need this. They have a definition, similar definition, but they need to be able to kind of pass through the origin. They need, at the moment at least, some algebraic torus contained in X minus D. Okay, so that was just a short wrap up. Took, of course, longer than I hoped for, of this intrinsic mirror symmetry construction. Okay, so then what do we want to do on the Floer series side? So there are quite a number. Maybe I should say that because I'm just seeing this here. One important thing is, of course, the whole thing is a family fiber over the spectrum of that ring that looked a little awful. This typical non-Noetherian ring of spec. Spec C or spec formal, depending if you work absolute or relative, or Q even, right? Q of NE of Y. So you get this proch or proch QH0 or spec QH0, spec formal QH0 over these two things. That's a local ring, so it has a closed fiber, and the closed fiber is the proch or spec of what is called the Stanley-Reisner ring. So whenever you have these kind of simplicial complexes, you get this Stanley-Reisner ring that essentially is the ring you see here. Okay, so whenever you have two integral points that are not in the same cell, it's just 0. And whenever you're in the same cell, it's just a monoid ring that you see from the integral points on one of these cones. Okay, so the central fiber, or the reduction model of the maximal ideal, is just a Stanley-Reisner ring. So QH0 XD mod M is the Stanley-Reisner ring of B as a spatial thing. Okay. So what are the third theoretic rings that we are interested in? I mean, of course, what we're really interested in. Oh, actually, first I should say, I prefer now to work in the relative situation. Yeah, you will see that some of the statements make sense also in the absolute situation. I have a little more clue of what to do in the relative situation. So we have these an analytic model now. Assume this. Proper column families. And what we are, of course, ultimately interested in is a Fukaya category of a general fiber. Well, let me write xt, t non-0. So, so the first thing is there should be a mirror object of the O of 1 bundle, or first of the O bundle, mirror to O. That should be an SYZ section of the SYZ fiber. I know how to obtain this very canonically if I assume that this thing has a real structure, and that occurs in any of the models I wrote down with Mark. We can always write them down with the real numbers. So in these situations, we would have some Lagrangian L0, which is just a real locus, a positive real locus. So there's a good sense in saying what that means. And it is a section of the SYZ fibration. Actually, it's homeomorphic to B. Not this B, actually. It's what we call, damn it. It's a B intersected with, not sure how to write this. Maybe if I want to homeomorph, I might just take B intersected with a sphere of large radius or something like this. Okay, just a homeomorphism statement. Okay, so that would be the SYZ section. And then we have monodromy that we always have. A symplectic monodromy. And then from these two things, I can build up all the other twists. So if I apply mu to L0, mu is like tensoring, is mirror to tensoring with O of 1. So I get all these other copies. So that gives L case mu k of L0, and that works for any k in Z. Okay, so you get this subcategory twist generated by the LKs in f of x. And the generation criteria that I mentioned in the beginning make a statement when this is actually a quasi-equivalence, an A infinity quasi-equivalence. So generation statement. So I'm giving the one that was given by Perutz and Sheridan. Based on Mohammed's work, and then there's another formulation, another proof by Ganatra. It says that if you have what they call core mirror symmetry, so if you know that we have an I infinity quasi-equivalence with well, that would actually be dB, right? That's an old one, which is a dB, or k. I mean, all k, right? So this is just dB, or y. Then we already know that LK is f of x. That's not equivalent. And then even better, we can get the A infinity structure on this guy by result of Polishchuk, which says that if I look at something like the ring structure you obtain for all these kind of positive things, so when you go from O of k to O of L with L larger than k, so this gives the homogeneous coordinate ring. O of, let's call D maybe, D larger or equal 0. So the ring structure says it suffices to check M2, which is the ring structure, for the homogeneous coordinate ring, respectively the corresponding mirror objects, plus 1 higher MK, plus 1 MK. I mean, I'm just an explicit MK. So that would have some sheets F1 to F0 to Fk. F1 to Fk. And showing that this is non-zero. Okay, so basically, what I want to say is that if we have full control of the homogeneous coordinate ring in our picture. And if we can show that these homogeneous coordinate rings, that this is the same as the ring structure you get on the corresponding Lagrangians, and monodromy translates of the Lagrangians, then we're done. That proves homological mirror symmetry. So of course, that still seems a little hard to work with these Lagrangians in complete generality. And maybe some other rings which I can then give to my symplectic geometry friends, and they will care about the rest of the equivalence might work better for me. So what are the other rings I believe should be isomorphic to these rings that we get here? So let me take as next one one that was suggested by Tim, are of mu. So that could be called something like the symplectic monodromy ring. I'm sure I discussed this with you, Mohammed, at some point too. It's a very cute thing. So you would just start with xt as a symplectic manifold and this monodromy. And then you build the symplectic mapping cylinder. Sorry, mapping torus, which is the xt cross r larger or equal 0 cross s1. Well, I shouldn't write it like this. Cross interval, and then I'd identify the two boundaries. Okay, so I want to view this as a symplectic fibration over r cross r larger or equal 0 cross s1, which is just C star. Okay, I will do origin. And then you can do Floer theory on this guy. Yeah, so you have these invariant points of the mu, and then you take Floer theory of this. Let me call this. Well, that would be actually xt and then mu2 minus r. This is counting holomorphic cylinders inside that symplectic mapping torus. For some reason, there is a change of sign that you need here. Okay, so that's the second trick. We may end up working with that at the moment. I mean, it's the setup I'll present is pretty insensitive what you do, what you feed in on one side, but at the moment I'm more hopeful in working with symplectic cohomology and proving that you actually get a ring isomorphism. Okay, so then the C, maybe it should have been B, is something that was featured in Denis' talk, is the red Foucault category. Now there's one problem here. Well, maybe it's not a problem, I don't know. There are various versions, of course, of Foucault categories here. The one that was suggested, was featured in talk by Denis, looks like this. So you would have, actually, maybe I should do it like this. So here is your xt. Or maybe the LT in xt, or LK in xt. And then you kind of wrap it around. And then you do these things to get something else. This is one version that you could work with. So this L0, so the LKs extend to LK tilde, so I was a little L in Denis' talk. Another thing that seems more natural for me, or closer to the way I'm thinking, or more hopeful to relate to anything that I know how to deal with, is to look at the extension, assuming we are working over R with a real locus. So that would be the real Lagrangian. That doesn't work really. So that would be the real Lagrangian. So that would just be we call it L tilde, so that's just XR. Presumably contains a little too much information because a real locus, what you really want is a positive real locus. But I don't know how to extend the positive real locus over that guy. So the only thing I can extend is an actual real locus, a total real locus, which has more components than what you care for. Okay, so this thing is expected to contain a little too much information. But it has the advantage that you can just work with real algebraic geometry to actually compute something. Okay, so there's presumably a version of real Gamma-Witten theory, puncture Gamma-Witten theory that you can use to try to relate it to this Floer theory and the corresponding ring structure you get. Okay, so and then finally the last one, and that's the one I will say a little more, which is which is close to the work of Ganatra and Homoliano, is this symplectic degree 0, cohomological degree 0, symplectic cohomology of this pair. So what would this be? So you have to change, of course, SH star of x comma d will be a direct limit of Floer homology groups of X with certain Hamiltonians. So the first thing that is a little worrisome is typical in symplectic cohomology, people would like some Liouville domain or something like this, so they can use compactness arguments, maximum principles. We cannot do that, okay? So the interesting cases are exactly where x minus d are not affine, okay? Of course, you could look at pair x comma d, x final or something like this, but at least in a degeneration case, that's very far from being affine, okay? It's proper over the disk. Or over the A1 curve. So you have to include d. Okay, so this will be a version of symplectic cohomology that contains stuff that lives entirely in D. Okay, so it's just a warning. So how then in so you may want to compare this with what's written in the paper of Ganatra and Homoliano, that in most of these papers, I should also mention, of course, Paskalev, who did that in the surface case before while I was at UT Austin. So typically you write down a very specific Hamiltonian argument, family of very specific Hamiltonians, and compute explicitly, okay? And then you get control over the generators. That doesn't seem a very viable way to do this. And from the definition point of view, there's not much reason for doing this. So we don't want if you work with virtual fundamental classes and compactness being assured from this map, from applying the maximum principle by composing this pi, so this is now a disk, there's no worry on compactness. So we can just write down this direct limit for certain H classes of H's which come by pullback from the base. Okay, so let's just do this. Should be totally insensitive to what I'm doing. And I wanted to extend over, so this is let's call this confusingly, maybe or not, T. Okay, so that should be some profile, doesn't matter much. And you order these by the maximum of this H prime. So they should get steeper and steeper. You achieve this by moving that value at 0 up and moving the support in. So and then you should still get these continuation maps for whenever you have an H1 and H2 appropriately scaled. And that will be a definition. Okay, so then the conjecture, maybe I'll put it up there. So we have two conjectures now. So first, all these rings obtained from A to D should all be isomorphic. So some of these are purely symplectic questions. Yeah. So for example, trying to understand how the symplectic monodromy ring relates to the Fukaya category product, or the symplectic monodromy ring relates to this.
You erased A. Which one was A?
The A was the Fukaya category of a general fiber.
The homogeneous coordinate, the part of the...
Yeah, so the ones you get from the positive twists. Okay? So in conjecture 2, let me just formulate it for SH0 that this symplectic version of symplectic cohomology of the total space is actually isomorphic to QH0XD. So, and Sheila and Daniel proved the version of this for the case where X is actually Fano, or X minus D affine, and asymptotically, okay? So just looking at essentially the degree 0 part and understanding how the generators are. Okay, so that's of course a whole juice in the story. Yeah, sure.
What's the relationship between the relative form and cohomology and the non-relative?
What's the question? What's the difference between the relative and the absolute quantum cohomology? It's totally different. Okay, so the absolute quantum cohomology can be pretty boring. The relative quantum cohomology always contains lots of information. Okay. I'm not saying quantum cohomology is boring. Okay, so I'm saying this thing. You know, I'm just doing well, where am I? QH upper 0. Okay, so if you do QH0 of anything, I mean that has only the one, right?
So can you always recover the quantum cohomology from your relative?
No, I mean not from this one. I mean of course there is something like QH upper star of X comma D, and that would contain the compact ones in there too. Sure. Yeah. So it's a kind of.
Substitute more or less like the wrong, because in some situations mere varieties are non-commutative, that like H20 algebras, Gradient algebras should be non-commutative, and when I go to symplectic you get on the commutative test. Yeah.
But I think by assuming that he has this real involution, it's probably gotten rid of non-commutativity.
Right, so exactly, there is certainly room also in our program for these twists, and simplify a little bit, okay. Yeah, right. At the moment, I'm making a statement about conjecture 2, I think. Yeah. Okay, so that one I'm pretty confident should be true the way it's stated. When you want to relate it to the Fukaya category, that gets a little, because you need at least a Lagrangian, right? Yeah. So, and without anything, I wouldn't know how to get that Lagrangian, and that's where this comes in. Okay, so let me then, so if you have lost track of what I'm doing here, let me wrap up. So what I was saying is, if you take conjecture 1 plus conjecture 2 plus one computation of the Massey product, higher Massey product, one single computation, okay, not the whole Massey product, just for one specific thing that I'm hopeful one can do, okay, plus mk of some Lagrangians, non-zero, L0, L1, whatever, or maybe L1, L2 to Lk is non-zero, that would reply homological mirror symmetry in this setup, okay? So in the rest of the talk, let me give a little bit of technical juice to this, to all these claims. So something on conjecture 2. So let me first, there are actually kind of two problems that can be solved independently. And for one, I might get help from a student of John Pardon, which would be good. So that's the project with Tim is to go from symplectic to complex analytic. So there's a version of these zeroth degree relative quantum cohomology that is just working in the analytic category, okay? It's a complex C analytic, okay? That's a trivial remark, okay? You just replace everything algebraic. You define this by working with a complex analytic, delete Mumford stacks, and blah, 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 okay? So that's not difficult. And the hard part is to prove that there should be an isomorphism here. Okay, so the idea is pretty obvious. You would have to count cylinders. So what you want is you want to write down a morphism from QH0 to SH0 by counting cylinders. In the usual fashion. So that would start kind of cigar-like picture. Confusingly, of course, the output comes in here, so that would be one periodic orbit. So X, maybe I should call it X, let's call it Z or something, okay? So this would be a periodic orbit. Okay, and then I have one outgoing point, P. So that would be a puncture, actually. How do you get these things? In the easiest, by working in the total space, I mean, what would this look like? So this is fibered over a disk. And then you can produce such cigars by taking kind of a little circle around that guy. But actually, maybe just for artistic purposes, let me draw it here. And then you have a little disk touching the center fiber at a point. Actually, most of these things will touch deeper points. Okay, so you take a multi-section through this of that thing, and that has a boundary, and that would be the periodic orbit, approximately. Okay, so these are the objects you count. Maybe something that is not obvious to many people in the room. If you do this, what you get at the center fiber, you can actually put a negative puncture in there. Okay, it looks positive, but it's actually a negative thing if you think of extending it to. So if you do something like this on the center fiber, take a component of the center fiber or some curve in the center fiber and connect it with some section, and then you remove that thing here, you get a puncture here. Okay? So these would be these punctures. And then to prove that this is actually well defined, so commutes with a differential. Of course, we have no differential here, yeah? So that was just because we just take the contact orders, yeah? But there would be, so there are no differentials here. But something could come up here. And in general, of course, you have to degenerate the thing, and you get all these bubbles on the center fiber. Whenever you have a bubble, it will be in the center fiber. So there will be a gluing theorem where you have to deal a little bit with these complex analytic models that you have on the center fiber with something more symplectic here. What do we do with the Hamiltonian? As a Hamiltonian, so there's always a kind of stabilizing of the domains, just contracting all the bubbles. So we can specify some cutoff function. So in the neighborhood of this outgoing point, there's no Hamiltonian, okay? This is pure complex analytic geometry. While out here, this is pure symplectic geometry, Okay. Unfortunately, John Parton has already done all the work to set up Hamiltonian Floer theory for this setup. And the pair of pans product, well, then to show it's a ring homomorphism, you have a similar idea in how to connect two incoming things with one outgoing thing. So for the ring homomorphism, you have to study diagrams like this.
I mean, I have to object that somehow this was set up by, Fukaya Ono 20 years ago. The Hamiltonian theory part. I understand you're saying you
Yeah, sure. I wanted no. I didn't. Gosh,
Sorry.
dangerous topics here. No, I didn't. I just want to say this is the John Parton thing is the thing that I can just push the button, and it has the kind of local model that I want to put in and use it. Of course, yeah, all this other work that we could also use. Okay, so this would be the ring homomorphism. Nothing is written on that, quite frankly. So I expect lots of kind of nitty-gritty details coming out once I start writing. And going back to the stuff I had done maybe 20 years ago, and I've forgotten largely. So I have like 8 minutes. So then there's this other thing, which kind of, maybe you are already happy with this kind of framework, but there's this other thing. If you use John Parton's approach to write down virtual fundamental classes in algebraic geometry or in complex analytic geometry, you would work with complex analytic models that are just given. So maybe I'll write this here. C framework. So that works with so here's your moduli space. And then you have some open subsets in here, U alpha or something, and then S alpha to E alpha, in such a way that these, sorry, that's wrong. So this is then contained in V alpha, and the S alpha goes to E alpha, and the U alpha is the zero locus, it's the preimage of zero of this S alpha. Okay, so you get local descriptions of your moduli, so of chunks of your local moduli space, complex analytically, in terms of holomorphic functions with some manifold. So this is a topological manifold. So that is all fine. It gives some virtual fundamental class, but that's not the way it's being done in algebraic geometry. Okay, and that's not the way Mark and I wrote down our rings. Rather, we use in algebraic geometry. So let me this would actually be from C analytic to algebraic. So we need to compare Parton's VFC framework in C analytic setup. Note that this is really C analytic now, right? We would be doing, where is it? That kind of thing, and compare it once you have bubbles over here. Yeah, so that would somehow be generated to something that looks like this, and then you have a 3-puncture sphere here. This is the kind of thing you have to look at. And that bubble, this is really now a PQR. That's the stuff that appears in my definition with Mark in QH0. So this lies in the central fiber. Okay? So, and of course the whole thing is a product. So you only care about what's happening here. With, let's say, Bernd-Van-Tekke's in algebraic geometry. So there's actually, John Pardon pointed out he has a student, let's get his last name right, Mohan Swaminathan. Whose thesis topic is to do this for Gromov-Witten theory. And he has apparently already advanced pretty much. I'm trying to convince him that he should not do it just in Gromov-Witten setup, but in full generality, okay? Just assuming you have some relative obstruction theory from M over some Artin stack, it's called A base Artin stack, which in Gromov-Witten theory would be the stack of pre-stable curves. And then you get the Bernd-Van-Tekke's definition, but you could as well do John Pardon's definition, okay? And so I have 3 minutes to give a few details on that. So what's the difference here? So in Bernd-Van-Tekke's, let me remind you, or even better if you have never heard of it, how this works. So how do we do it in algebraic geometry? You would have, again, an embedding of an open subset inside some smooth space. That would be my V alpha before. Okay, let me drop some alphas. Okay, so this is, I don't care if it's a zero locus of a function or something. You could always set it up like this once you have an obstruction theory, and then you obtain a normal cone, which is just a relative spec of I to d mod I to d plus 1, where I is the ideal defining, sorry, that's wrong, the embedding of U in V. And that sits as a closed subcone inside the normal linear fiber space given by the normal sheaf. That's not a vector bundle, can change dimension, but who cares? And the point of writing down an abstraction theory in the sense of Bernd-Van-Tekke is to embed that situation into a vector bundle. Okay, so you would have an abstraction theory, the morphism in the derived category f minus 1 to f0 to the truncation of the cotangent complex so that's I mod I squared locally. That's locally just, okay? So that's a truncation of, gosh, I want to write something different. This is a cotangent complex of M over A. And that would be I mod I squared, so this is locally, to omega M over A, not M over A, V over A, restricted to M. Given that thing, you get a diagram of linear fiber spaces that looks like this. So here you have the tangent bundle of V, relative tangent bundle restricted to M. That goes to the normal bundle of V over of U in V. So here's your normal cone. And then this goes to F0 and F1, which are the corresponding linear fiber spaces. And then what you do is you construct this cone by taking the image here and making it invariant in the F0. So something like F0 plus the image of CU in V. That might not be injective, but who cares? F0 acts on this. And then the virtual fundamental class is given by the intersection with the zero section. So this sits inside F1. It's a cone bundle. So then you write down M Birch as C intersected zero section. Now what I suggest to do is, I mean, how does this arise if you think of a section of a vector bundle? There's something called deformation to the normal cone. So essentially it means you scale your section and take the limit. And that produces a rational equivalence of this normal cone of the zero section inside your, that would be the V here, with a cone inside, or rather the graph of your section with the cone inside the vector bundle. So and I suggest and that should be possible, to incorporate that kind of deformation to the normal cone inside John Parton's framework.
It's built into his framework. He already uses deformation to the normal cone in the topological category.
Not quite this one.
Okay.
I know that, yeah. Okay, so that was it. And hopefully at some point in the future, some of this will actually surface into a paper. Thank you for your attention.
Just remark, I think now the better approach is very different is this Adil Khan and some other people, which much more clear, it will be easy to compare with.
Who is this?
Adil Khan. Adil, K-H-A-N.
Okay.
There's not only one, there's another guy, so there are
Okay.
2-3 competing approaches, which is much better than
This is what, like the derived geometry approach?
Derived geometry, yeah.
I see.
Yeah, okay.
No, but it's really simple in the sense here. It's not.
I'm just okay. I'm always happy to take whatever approach is around,
Yeah.
but
Well,
it would mean I have to redo all of puncture gamma bitten theory and logarithmic bitten theory in the derived framework.
No, the problem is it's a proof comparison, but it's kind of easy to use. Yeah.
Okay. Yeah, it's possible, but it's not very hard actually. I mean, I did this comparison a long time ago, 20 years ago, with my framework, and I certainly know how to do this. Anyway, okay, but yeah.
Any other questions? Well, it's in Bernd again. I'm back in 2 hours.